Example, heat transfer 1. What must be the temperature of the coolant to cool 500 kilograms of a substance from 140 degrees Celsius to 60 degrees Celsius in 1 hour? Assume the area of heat transfer is 1 meter squared. The coefficient of heat transfer is 500 watts per meter squared Kelvin, and the specific heat capacity of the substance is 3.6 kilojoules kilogram Kelvin. Okay, what formula do we have? This is a standard formula using M and CP and U and all those. We have M times CP times the change in the temperature over the change in time is equal to minus U times A times T minus TP. This is our coolant. And a lot of times this is written with the minus inside, but it's so much easier to integrate if there's no minuses. So we're going to leave it like this. And we have a separable differential equation. We have initial conditions. We have values for all the different things. So let's just go and solve the differential equation in its general form, separable. In fact, there's no T anywhere. There's just capital T for temperature. So let's write that correctly. So we would have dt over T minus Tp equals minus UA over M times Cp times d time. Integrate both sides, and we have, these are all constants, and we get ln of T minus Tp. That's the easy part if you don't put the minus. That's the part that I like. Minus U times A over M times Cp times T plus some kind of constant C, fancy prime, whatever you want to write it. And since we're interested in getting to Tp, the primary coolant, probably we would like to get rid of Ln. So let's do E to both sides. So we would get T minus Tp equals E to the minus U times A over M times Cp times T plus C fancy 1 prime. And this is E to this times E to that. So that E to this part we will write C double prime. So we get as our first general solution T minus Tp equals C double prime, that's that E to the C prime, times E to the minus UA MCP T. So this is our general solution. And then we're going to put in our initial. Initial means T equal to 0. At T equal to 0, we have temperature is T0, and in our case it is 140 degrees Celsius. Right now we're just going to use this, and when we get to the end, we will put in all of our numbers and check all of our units. So we are solving for C double prime, the constant of integration. So we have T0 here, and then minus Tp equals fancy C double prime E to the minus UA MCP times 0. So this is all 1. And what do we get then? We get C fancy double prime equals T0 minus Tp. So we would put that into this to get our final solution there. And that would be T minus Tp equals T0 minus Tp E to the minus U times A over MCP times T. So that's our function for the temperature as a function of time. So let's work on our numbers. M equals 500 kilograms. Cp equals 3.6 kilojoule versus kilogram Kelvin. We're going to have joules, so let's write that as 3612 joules versus kilograms Kelvin. So these kilograms will cross those kilograms. The other joule, how we're going to get that? U is 500 watts versus meters squared Kelvin. Watt is a joule versus second, so 500 joule versus second meter squared Kelvin. A is 1 meter squared. So we have minus UA over MCP equals minus 500 joules versus seconds meters squared Kelvin times 1 meter squared, there goes the meter squared, over M, 500 kilograms, the 500s will cancel, and CP is 3,600 joules versus kilogram Kelvin. So what cancels here? 500 with 500 cancels, joules with joules cancels, meter squared, meter squared. This Kelvin is on the bottom, that Kelvin is on the bottom. So we have this Kelvin with this Kelvin, and kilograms with kilograms. So we are left with, so we have equals minus, and I see 1 over seconds on the top, and 3,600 here. So what we have is minus 1 over 3,600 seconds. Okay. Now, what piece of information have we not used? And for time, we have T0 equals 140 degrees Celsius, and T ending is equal to 1 hour, is equal to 3,600 seconds, and T, the temperature at the end, which is T of T end, is 60 degrees Celsius. So we have a number to substitute here, this one. T is going to be TE, 3,600 here. That gives us our 60 degrees over here. And we know that T0 is 140, and we can solve for TP. Let's go for it. So we're substituting for time TE. So we have 60 degrees Celsius minus TP equals 140 degrees Celsius minus TP. Then we have e to the minus 1 over 3,600 seconds times 3,600 seconds. How convenient. And so we have 60 minus TP. We'll write it without the units because we got all our units straight. 140 minus TP times e to the minus 1. Get our calculator. How did we get e to the minus 1? So that's 1 plus minus, that's minus 1, and then we need inverse ln. So it's 0.3679. So we have 60 minus TP equals 140 minus TP times 0.368. So let's clean this up. So what exactly do we have? We have 60 minus TP equals 140 times that. So get our thing up here. Times, let's put that in the memory store, times 140 equals 51.5 minus 0.368 TP. So we have 60 minus 51.5 equals TP minus 0.368 TP. So this is 8.5 equals TP times, and we need 1 minus 0.368. So I believe that was in our memory. So memory recall, plus minus plus 1 equals 632. So 8.5 equals TP times 0.632. And now we just need to get TP is equal to 8.5 divided by 0.632 equals So 1 over x, and then times 8.5. 13.45 degrees. 13.45, and we remember that it's degrees Celsius. So that is our final answer, the temperature of the coolant. That makes sense. It has to be under 60, obviously, to cool it. And it has to be reasonably low in order to cool reasonably fast. In 1 hour, it has to reduce it by 80 degrees, right? So in 1 hour, we are going to use a coolant that's 13.45 degrees Celsius to cool our substance from 140 to 60.